Okay, welcome back. In the last lecture, we were dealing with image segmentation using graph theory, something called normalized cut algorithm. It was an algorithm where we were defining a function, a matrix called normalized graph Laplacian. Okay, let's remember how it was. There was this matrix, this L matrix is defined as D minus W, and D matrix is nothing but the sum of the affinities in the diagonals, okay? We have these things zeros here, and we are subtracting from the uh, affinity matrix where the diagonal entries are zeros, whereas all the others are, these Wij's are giving us at the ijth location the similarity between the ith node and the jth node, okay? Now, this was our fundamental thing, and this is the unnormalized version. Our algorithm at the end gave us the result. It's normalized version, okay? It's normalized version, which is multiplied with the square root of this D matrix. Its normalized version is giving us the eigenvector corresponding to the second minimum eigenvalue was giving us nothing but the positions of two different clusters. Please note that we were trying to minimize nothing but such a term where we are talking about this is L, this is this one, and F, D, F. We were talking about this one, okay? Now, we were trying to minimize this, and now, this minimization turned out to be the thing I have told you, which is the normalized Laplacian L tilde operator, okay? And we were at that point stopped one point which is we were able to obtain a vector where the positive entries are our the one cluster A, one segment A, and the other negative entries are cluster B. Therefore, at the end, we find the eigenvector, we threshold it simply, and based on positive and negative values, we just obtain nothing but our two different clusters. But the natural question at this point arises, I would like to segment my image or data into multiple clusters. What I'm gonna do at that point? Well, one possible approach, the normalized cut algorithm, can be applied iteratively after determining the most dense similar cluster. The remaining data an affinity matrix just specific for this remaining data can be written. The Laplacian, the normalized Laplacian can be obtained for the remaining data. And the same procedure can be applied. That's one typical approach. Therefore, it's a little bit slow because you just do it 2 by 2 and you continue like that. But another approach is spectral clustering. Now, I'm going to tell you what is spectral clustering. Before moving into that, I would like to remind one little thing for you. Please note here, if this L matrix is multiplied with a constant 1 vector, okay, which means effectively D is multiplied with 1s. I think previous hour I did this, but I'm doing once again. If I have this, such a term, please note this is diagonal. Those diagonals at the end give you nothing but the summations here, this D1, okay, D2, you have these things, okay? These are nothing but your summations, Wij's, which are equal to your corresponding, this is 1J, 2J, it goes on like this. Now, the other one, By the way, if you just multiply this thing with only ones, please note that that exactly gives me the same result here. Therefore, we should always remember this fact. This is exactly equal to 0. Therefore, the Laplacian multiplied with constant ones are giving us zeros. In fact, we were talking about that's an eigenvector because the eigenvalue is 0 for this case. Now, what I'm trying to explain at this point is for any connected graph, the thing I'm writing over there is always true. Okay, it's always true. Therefore, Laplacian multiplied with constant ones are giving me a beautiful 0 over there. Therefore, our smallest eigenvalue is always 0 for connected, totally connected graphs. Now, today I'm going to continue, or in this video, I'm going to continue with this idea. Now, I would like to extend my thing into K clusters, and I'm going to show you one little example here. One-dimensional example, some scalar numbers. Some numbers are between 2, around 2, some of them around 4, 6, and 8. It goes on like this. There are 4 clusters, one-dimensional scalar data. These are the number of occurrences. Everyone can see that there is one cluster here around 2, another cluster 4, 6, 8. Now, if you just obtain an affinity matrix for this particular problem in terms of the distances, obviously, for every data, the differences between the values, obviously. Maybe there is, for example, let's call there are 40, 10, 10, 10, 40 data that we have. If you look to the first eigenvector, as expected, it's constant. This is, by the way, this 246 is wrong. This is nothing but the number of samples here. It's assuming it's 40, for example. It's 1 to 40. All the elements of your eigenvector is constant, just like this constant here. Okay, this is something expected because we know that it will be constant, and because they are connected, all of them have some relations. Now the second one, this is the one we have learned in the normalized cut. If you just divide from here, the positive ones is one group, assuming they are indexed like 1 to 10, 11 to 20. These one, the first 20 ones, these are the last 20 ones. These values are showing us these two groups, and the negative values are showing the other group. In other words, the eigenvector 2, the eigenvector corresponding to the second minimum eigenvalue, this guy, non-zero one, which is giving positive and the negative values, and we are making clustering through this. In other words, these two is one cluster, these two is another cluster. Let's continue to look for the third eigenvector. If you look at this eigenvector, we will see that some of them are positive here, some of them are negative here, some of them also negative here, some of them are positive here. In other words, these guys were dividing 1, 2 clusters from 3, 4 clusters. This is giving more extra information for us. It's in a way that it is giving us that, for example, these two are different from here. In other words, if you look, put a threshold here, these guys will be maybe belonging to this one, and those guys belonging to this one. What we are observing is this. In fact, the other eigenvectors, the corresponding values, positive, negative, whatever they are, together with all the eigenvectors, they are giving us some information. For this eigenvector, being positive is these two. For this eigenvector, being positive is this and that. Negative maybe these two. Therefore, from this information, I am able to, gathering these information together, I am able to obtain the individual clusters one by one. In other words, looking positive, positive, 1 to 10, one cluster, positive, negative, second cluster, negative, negative, third cluster, negative, positive, for example, fourth cluster. Okay, therefore what I'm seeing here is I can use this information to obtain some clustering, not only for only two clusters, but more than this. Let's look at this idea in a more careful way. Okay, now if the graph is connected as I shown you here, okay, I've shown you here, the minimum eigenvalue lambda is equal to 0, the Laplacian is equal to 0, therefore we have an eigenvector of constant ones, and that's one thing we have learned. This is useless for us because it simply says everything is a one graph. Hey, this is useless. Now, the concept is if we have k connected components like here, let's assume, for example, these kind of things, all of them are connected, but they are disconnected from this green ones. Green ones are disconnected from the blue ones. What does this connection mean in terms of a Laplacian matrix or an affinity matrix? Between L1 to L2, let's assume L1 is this guy, L2 is the green one, and L3 maybe the blue one, okay? Or vice versa. This is the green one, larger, L2 is the blue one. Now, what I'm saying is this. Except for these matrices, the affinities should be exactly equal to 0. There shouldn't be connection between these guys. There shouldn't be connection between blue and green, green and red. Nothing as a connection in between. Okay? Therefore, our aim here is finding some result in such a way that there are some submatrices, and those submatrices are indicating our connected components. In other words, clusters. Obviously, I don't know anything connected or not in the beginning. I have only this formulation, but in a toy example, I am realizing that connected things will give you some non-zero values. Everywhere else between these submatrices, we will have all zeros. Now, please note here, if I multiply this thing with this 1, with this sizes here, the width is this ones, everything else is 0. This, if you multiply this one with that one, please note that that will also give you a beautiful 0. All the terms this L1 will be multiplied with ones, okay? And all the others will be 0. And in this way, please note that as before here, I'm not doing once again, this connected subgraph multiplied with ones will give you a beautiful 0 for Laplacian inside. Similarly, this one will make this one 0, that one. Now, what did I learn? If I have 3 connected components, as in these toy examples, this one or that one, again, the first 3 eigenvectors also will be consisting of these kind of entries and gives you nothing but zeros. We learned something from here. If you have multiple clusters, those multiple clusters will give you these kind of eigenvectors, non-zero sum of the terms, 0 for the other terms, ideally. But please note that maybe you remember we have a relaxation step during this solution. We have the normalized Laplacian. That normalized Laplacian no more makes you perfect solutions like this, but you need a relaxation. Then you say not 1, 0, positive or negative values. Now, what did we learn from now? Looking to this Laplacian, having these kind of submatrices, and the eigenvectors correspondingly is giving us the positions, the information about the every data. Let's start with, for example, the first index here, belonging to the first cluster L1 or 1, cluster 1. Now what we are seeing is this, 1, 0, 0. This entry for the first eigenvector it should be 1. For the second one it should be 0. For the third one it should be 0. How about this guy? This guy says for the first one it should be 0. For the second one, it should be 1. For the third one, it should be 0. Hey, the information about the label of these clusters are stored in the eigenvector entries. Let's make an algorithm out of this. And let's look at this one. Very simple. 2 by 2, 2 by 2, perfect case. This is just our constant 0, 0 constant. 2 eigenvectors. If you multiply them, it will be satisfying the eigenanalysis. They have the eigenvalues, both of them equal to 0. If it is loosely connected, 2 clusters, some very small off-block entries like 0.2, 0.1. Your eigencell will not give you this. But look at the result. Positive, positive, first vector, first vector. These two guys, positive, positive, 0.5, 0.52. Now for these guys, positive, negative, positive, negative. They are giving us, they are signaling us the first and the second node is one cluster belonging to the same similar values, and similarly here. Not exactly like this, positive 0, 0, positive, but positive, positive, or positive, negative, they are giving us some information. In other words, in the feature space, they are showing us where they are. This is cluster 1, the red's going to here in this new dimensions. And this is these two going here. Please note, looking to these new vector of size 2, this one component, this is the other component. The first sample is represented, whatever it was previously represented by, but right now, two-dimensional vector, two-dimensional vector, two-dimensional vector, two-dimensional vector. And more importantly, in this two-dimensional space, they are separated very well. Now, how do we do it? Build your similarity matrix. Compute your first k eigenvectors of this Laplacian. Build a matrix V, a new matrix. Eigenvectors as columns. Eigenvector 1, eigenvector 2, eigenvector 3. Okay? Now, the first node, it will be represented by Z1 vector, and Z1 has this component, the first component, the second component, and the third component. If you do so, your nodes are mapped to this three-dimensional space, whatever it was initially, and more importantly, it is very likely that the clusters together are in very different positions, easy to cluster. Now, what is the final step? Yes, cluster these points, Z1, Zn, in this three-dimensional world using any well-known algorithm like k-means or whatever, and let's solve in this problem like this. Let's look at some simulation results. Such a problem, two-dimensional feature space, one cluster here, another cluster there. Therefore, everyone is seeing that these are two distinctive clusters. Now, what we are saying at this point is, well, the k-means algorithm for k is 2 and the spectral clustering with only a single one, normalized cut, they will perform more or less the same. They will perform more or less the same. Okay? Now, but if you go to such a data, yes, there are clusters. One cluster here, like a core, the other one is the outside. Really different. The k-means don't work. This is what k-means do. Just try to divide somewhere here. Very bad results. This is what your spectral clustering will achieve. Okay? Therefore, please note, such a different clustering problem can be achieved by using such a spectral clustering algorithm. If you have the previous thing, three distinct results, like three distinct clusters, cluster 1, cluster 2, cluster 3. If you say, hey, I know that I have three clusters using three eigenvectors, if you obtain your results, obviously don't forget the first one is gone, the first one is constant, the second, third, fourth, it will be like that. You will have nothing but this result, okay? And similarly, if you go and solve the same problem, not 3, but 2 clusters, it will be, you will obtain the result something like that, okay? And one cluster here inside, all 2 others are going there. The k-means will do it in a very different, maybe undesired way, but here we obtain relatively good results. Now, maybe the final question is, okay, how do I select k? Until now, k-means has a problem for that. RSSD was the graph theoretical approach, don't know where to stop. Now we have an answer for this. Look at the previous results that we have. I was saying that based on the number of clusters, you will have 3 eigenvalues and the corresponding eigenvectors. In the ideal case, 3 zero eigenvalues. 3 zero eigenvalues and the corresponding eigenvectors. Okay, never in real life, you don't have these kind of really disjoint sets, but something similar to that. The eigenvalues should have a very important information for that. Let's look at the example here. This is called the eigengap, the difference between consecutive eigenvalues. Okay, the previous histogram sample, a very clear 4 clusters. Look at the corresponding eigenvalue. The first one is 0. Every time, everything is connected, therefore it's a 0. But 2, 3, and 4, they are basically saying that very small values with respect to the 5, 6, 7, and continue like that. Okay, there is a gap here. If you look to the consecutive differences between the eigenvalues, absolute differences, this subtracted from here, this subtracted from here, this subtracted from here, at some point there will be an important gap. This gap is a very good indicator of the total number of clusters that your data have. Okay, therefore that gap could be utilized for our purposes. Okay, now that concludes our discussion about graph theoretic approaches. The graph theoretic segmentation, the first one was RSSD, something simple old. The second one was normalized cut, and the extension to the normalized cut was the spectral clustering. Normalized cut was doing this thing by only having dividing into 2 parts. I just extended this one, dividing into multiple segments, and moreover, I am also giving an idea how many clusters that I can have through such an analysis. That was a beautiful algorithm. Now we are opening a new part in the image segmentation. It will be a final subsection that we will analyze, and this time we will do everything using probabilistic models, not graph theory. Therefore, this time I'm going to use probability theory. There will be 2 main algorithms. Okay. Obviously, people are doing lots of things using probabilistic models. Statistical signal processing is basically devoted to this concept. Therefore, you can assume your pixels are also basically intensities are observed through some probabilistic structure. The labels, the unknown labels of every pixel, the object number, cluster number, can also be basically assumed to be a random concept, and we can just try to solve these things through such probabilistic models. Okay, I'm going to show you 2 algorithms, 2 main fundamental things. One of them is the famous mean shift. Okay, mean shift clustering, mean shift segmentation. That's a very interesting algorithm. I'm going to just show you how do we do that. The second one will be a little bit larger and longer. Maybe in the next video I'm going to talk about this. Segmentation using probabilistic graphical models, and the most important, the famous Markov random fields. I'm going to show you how to apply these things. Normalized cut is beautiful, very elegant algorithm. Mean shift is very popular, simple, elegant again. But to tell the truth, according to my information, my knowledge, uh, among all the other techniques, if you just don't consider the complexity, this macro random field base of things is the best uh, algorithm that you can obtain for segmentation quality. That's the most preferred one if you don't have time constraints. I'm going to explain later in the next slide, but next video. Let's start with talking about this mean shift algorithm. I'm gonna again explain everything using a toy example where we have some data. I'm trying to obtain some data, a generated data here, okay? And this data is coming from a PDF, a probability distribution. Okay, therefore, let's assume a two-dimensional case, and this probabilistic model brings more data from this X and Y, such this, and a little bit less from here, and for all the other parts, it is creating less data. Please note it's like a random variable. This is just showing us what is the probability of observing something with this XY, with this XY, and I'm giving you the observed data samples at the end through something like this. In real life, we observe samples. From the observed samples, we will try to find the PDF. Why should I find the PDF? What is the relation to segmentation clustering? There are these data, these samples are sitting here. What could be the reason that I'm going to estimate a PDF, and that PDF will tell me the clusters? Now, the idea is this: the observed data is sampled from an unknown PDF. I will try to estimate it. And at the end, I'm going to say, use samples. These samples are due to this peak of the PDF. Those samples are due to that peak of the PDF. In other words, I am assuming my PDF is consisting of some sub-conditional PDFs, and the sum of them I am observing it. I'm just trying to observe which samples are coming from which part of this PDF, like a mixture of Gaussian or mixture of something, mixture of some other PDFs, and I'm trying to find this data coming from here and that data coming from there. Now, oops, what happened? Well, I don't know. Something happened to our... Let's just wait a second. I'm just trying to... Yeah, good result. Let's continue. Okay, now what I'm doing here is... the first thing is I am just trying to obtain where the data is coming from. Mean shift is a very interesting method. Determining the modes. Mode means peak points of a probability density function. PDF is short for probability density function. And those PDF peaks I'm trying to obtain so that I'm going to say you belong to this peak, you belong to that peak, and you belong, for example, something else. Each data belongs to a single mode. This is the clustering concept. This is the segmentation concept. We are trying to obtain the probabilistic source, which is generating this part, which is generating that part. Now, one little thing to note here. Any function, the local maximum is pointed by the gradient vector. What do I mean by that? Okay, just consider this. A function like that, this is the peak point. At any instant, okay, this is your slope, a positive slope here, and here you have a negative slope here, okay? This is your negative slope. Now, what I'm saying is this. At this point, x1, and at that point x2. The peak is at x3. The positive says you have to go in the positive direction. The slope is giving me the position where the peak is. And here at x2, you are saying that you have to go in the negative direction. Therefore, this slope, this gradient, is giving me the direction where to go. That's a general concept. If you are interested with the peaks of a PDF, you will go and calculate the gradient, the slope. Obviously, multidimensional, two-dimensional, we have a gradient. You have to find the gradient of this PDF and the gradient vector. This is like a positive or negative scalar here, but in two-dimensional or multiple dimensions, we have a plot and we have a vector, and that vector will show me nothing but the direction of the peak. Therefore, if I can estimate the PDF of the data, and if I take the gradient of it, the gradient vector at any point, for example, the gradient point at this point will show me this is the direction. That will show me this is the direction. That will show me this is the direction. I have to find PDF, the gradient of the PDF. At every point, the vector will show me the peak. And the samples showing the same peak are belonging to the same cluster. That will be the rule of the game, okay? Now let's do it mathematically. Although I'm not showing in this course, in pattern recognition, in maybe probability theory, it's very well known that from the samples you can estimate a PDF function. Now let's assume I have this PDF. These are my samples, one-dimensional data. Now, one typical technique is this. You have a kernel function like this. Let's call this, I think, with x, k, sorry. This is just like a kernel, like a Gaussian type of thing here. Now, what you're going to do is you will just have the shifted versions, x1, x2, kxn, and you just plot these things like that. At every sample that you have, if you have 1, 2, 3, 4, 5, these samples, if you just obtain this, and if you add them up, if you add all your kx minus xi for I1 to n, that will be nothing but such a beautiful thing at the end. It's not a very clear thing. Let me draw it once again. It will be like this, one peak here, maybe another peak there. These are the points where you have lots of data. Now this is a beautiful approximation, and this is a well-known approximation of your PDF, okay? Therefore, that's the trick. People use it a lot, which is called kernel density estimation. Using kernel density estimation, any PDF can be obtained, can be estimated from the data. Now, this is your PDF, okay, x minus xi. This is your kernel function. Please note that this kernel function itself has a parameter like h here, okay? This is your h parameter. You don't know what will be the width of your kernel, this Gaussian type of thing, okay? And obviously you are just taking this thing as a norm. Between x and xi, there will be a norm, and that norm difference divided by h is your normalization factor, and you just go and write it in this form. Now, please note, my aim is calculating the gradient because the gradient of any function shows the mode, peak. If you know the peak, you know which cluster the sample is belonging to. Now, I have to find the gradient. The gradient of who? The gradient of f of x. If you take the gradient of this, the gradient operator will go inside. It's a linear operator, and you will take the k, or you will take this k operator like that. Okay? Now, if you just take this derivative, okay, here, just assume this is minus g. If you write it like a minus g, the derivative of this k is written as a minus g function. Here, you will have, instead of x minus xi, it will be xi minus x, and you will have this g here, okay? Now, you will understand why I'm doing this little trick. But at the end, I obtain this x minus xi is due to the derivation of this thing, the thing inside, okay? The x minus xi is due to this one. And taking the derivative of this thing with respect to x, that x minus xi will go out. And you will also have this minus, due to this minus g here, and you have this kind of xi minus x, okay? Now, you obtain the gradient of your f function with respect to this x. X is a vector. I don't know the dimension of it. Okay? Now, if you just write this, if you just write this term, I can define this m function. Please look at this m. I'm going to write it here. I have this thing here. This is like your derivative x minus xi. Okay? And let's write the m function here. Xi gx minus xi divided by the summation of this thing. Okay? This is your m. This is your m vector, obviously. Okay? Now, this is m is equal to like this one. This is the whole thing is m. And I have this thing at the end. Now, please multiply this one with that one. They will cancel out. But this one with that one will give you two terms like this. And I think this is what we are, isn't it? This is what is this upper part is equal to. Therefore, this is equal to nothing but this part. This part. Okay. Now, what is this vector? Let's look at this carefully. This is nothing but a weighted sum of the samples. And at the end, you are dividing them to the number of the sum of the weights. This means such a process is nothing but a weighted average of the samples. The weighted average of the samples, okay, this is the weighted average of the samples. And this is the point where you are interested about x. You would like to find the gradient of this point. X is your current point. M of x is showing the weighted average subtracted from this x. Therefore, what I'm doing is this. There is an x point I am interested. Around this x point, I calculated a weighted sum using a window. The window around this x point. You calculate some weighted sum, and that weighted sum subtracted from the current point is giving us this m vector. Okay? Now let's look at this m vector. This m vector was here. This part is a scalar. This is a vector. This part is a vector. Therefore, scalar vector, what I'm saying is this. My gradient is obtained in terms of m of x vector. Multiply with a scalar. What is this m of x vector? M of x vector is the difference between the weighted sum of the data around x, of the samples, and the position of x. Okay, now if you look at this carefully, you will see that this is the X point that you are trying to reach. You are at this point and you are trying to find this is your KX, this initial thing. This is G of X. These are XK samples. These are your samples. And from those samples, with these things, you are taking a weighted average. And the weighted average at the end is giving you nothing but a number, and that number is basically your vector. This vector is showing us where to. This is a one-dimensional thing, therefore your m vector is showing positive direction. Now, this a little bit may be complicated as a mathematical derivation, but let's look at the algorithm. This mx vector is called mean shift. The mean shift, we are shifting the mean, and the mode that we are trying to find for this f of x is obtained iteratively using mean shift vector. Now let me explain what do I mean by iteratively obtaining. What I'm going to do is this. I'm going to start with a y point. I'm going to start with a y point. Then I'm trying to understand where is the peak of this y. Okay, now what I'm gonna do is this. I'm gonna just basically find the weighted sum around this y point. I'm gonna find the corresponding weighted sum, and I'm gonna add on top of this previous yk this m. Okay, and I'm gonna continue in this way. Okay, let me show as an algorithmic way. It will be much easier to understand. First of all, let me show what's going on here. Let's start from here. There is a window. This red is our window. The window is moving around. We are only calculating the mean inside the point inside this window. And more importantly, after we calculate the mean value, we are basically shifting, mean shift. We are shifting the current position of our red circle to the mean value that I have calculated. Therefore, starting from a window size, an initial selection, every point will be your initial selection because you would like to see where this point is heading to as a mode. You compute your mean location, just nothing but the average of the samples inside, and then shift your window to the new mean that you computed in the previous step. And you will just do it until you obtain this result. Therefore, we basically obtain nothing but our mode for every sample that we have. Like this, for example, this sample goes to here. I am sure that that sample will also go to there. That sample will also go to there. At some point, I'm going to say, you guys all belong to the first cluster. For example, maybe some of them will go to another cluster. But for image segmentation, we need a trick. Until now, there were some dots, like data from your arbitrary values of your XY points, but intensities, how I'm going to do it in a pixel in an image. The trick is this. Let me show it. One dimension. These are your like intensities 0, 1, 2, 3 pixels, 4, 5, 6. These are bright pixels. These are dark pixels. Okay, I hope these are visible to you, huh? These are your dark and bright pixels. Now, the trick is this. You will have, this is your x-axis pixel. This is your intensity. Your 2D data will be x versus ix. Your window will be nothing but something around this. You will put this one and you will put a circle here, or vice versa. You will put this data here, the same circle will be put there, or here you will put the data here and you will put the circle here. Please note, this is the first time your X spatial coordinates and your IX image intensities are together in a same space, okay? We have a search window, like a circular 2D search window. Now what I'm gonna do is this. I'm gonna calculate the average of this one and that one in this two-dimensional. I move it here, I move it here. But please note that due to this gap and due to the size of this circle, this one will never jump, will never use any data from here. For example, this guy will also be maybe around here. You will also have such a data. You will never consider this data while you are calculating the average of this or vice versa. This is the trick while you are doing image segmentation. Let me show you some typical result. You're imaging into some features, into an n-dimensional vector. Please note you are also putting the special dimensions into your problem as I have explained in my notes here, okay? And you just compute again the average of the data, you compute the mean shift, okay? And then you move your window over there and you just try to reach a peak. When you have a peak, the algorithm stops. It doesn't go anywhere. Okay? Now the data, the samples, the pixels reaching to the same point in this 2D world, okay, same point in this 2D world will be nothing but your cluster, same clusters. Again, a 2D example, this algorithm says this is one data group. This is this peak, this guy here. This one is this blue one, okay? This ridge is these guys here. This peak is blue peak. This is nothing but my huge peak here. It goes on like this, and the data is obtained in this way. This is a very famous technique. This technique is applied to image segmentation, optic flow, data clustering. Okay, this is because a very fundamental thing. Random variables are their modes. We find their PDF peaks. You can utilize it in different places by the very simple technique. And if you look at the technique once again, these are the image results. This image is converted into here, like cartoon-like result. All these things are belong to giving, these are the peak value, I think. And this green grass is giving around here the same value. And this is around the same value. This is another value. And these are the results for your mean shift segmentation algorithm. Through this, you are finding the result. The only parameter, the only unknown parameter that I'm using, the only unknown parameter I'm using until now is my